In this first lab video, we will be looking at an example of motion with constant velocity as represented by a film of a soccer ball. We will evaluate the underlying physics principles and compare the motion to a model using Python of the same type of motion under ideal conditions. First, let us take a look at some of the fundamental principles of physics underlying this basic motion. First, you have Newton's second law. The net force is equal to mass times acceleration, which can then be rewritten in terms of acceleration. When combined with the equation for final velocity equaling initial velocity plus acceleration times the change in time, you have a general formula relating initial velocity, net force, mass, and time to give you a final velocity. Now, any object at constant velocity has a net force of 0, making the equation seen above simply reduced to final velocity is equal to initial velocity. Why is the net force on an object at constant velocity always equal to 0? Allow me to explain. In this case, we have an object that is currently moving in the negative x direction on this plane and has a net force of 0. Now, an object with already has a velocity in the negative x direction, if it then has a net force also in the negative x direction, it will begin accelerating rather than keeping constant velocity. Whereas an object still moving in the negative x direction with a net force then applied to it in the positive x direction will at first decelerate and potentially, if the force is continued, begin to change directions. Now let's take a look at the actual video being used to create our model. As you can see, it's a really simple video, near constant velocity as the ball rolls across the plane of view of the camera. So now if we take this video and we put it into this tracker program, we can track the motion at the individual points in the middle of its motion, because we want to ignore the beginning when it's accelerating and ignore the end when it goes off screen. So we track the motion the best we can. It gives us this nice little plot and a table of data, which we can then compare to our model. This table of data can then be copied into a spreadsheet as seen, which can be manipulated to create graphs and more directly compare to other sets of data. Now, the first thing you can do with this data is find the initial velocity, which you're going to need for your Python model. How you find that is by taking the first recorded value and subtracting the position, and then subtracting the initial position, and then dividing that by the first recorded time minus the initial time, which presumably will be 0. You should also take note while here of the last time that you recorded, because you will also need that for your Python model. Now over in VIDLE you can see the Python code used to create the model and some important key elements such as the mass of the ball which was recorded, the initial position from the tracker simulation, and the initial velocity as calculated in the spreadsheet. The final time that you want the model to go to is also inputted. An important thing to note is that the net force vector for this constant velocity model is all 0. When run, this model will behave as such. As you can see, much like happened in the actual experimental simulation, the ball begins at the origin and moves in the negative x direction, while the graph of position has a constant downward slope representing the constant velocity. This Python model also outputs a data table of all of the values, which we will then compare to our experimental model. Back in our spreadsheet, you can see we still have the experimental data and the graph of it, and then in addition now has been added the model data and the graph, which as you can tell already appears more linear. It's a lot easier to see, however, when they are graphed together on the same set of axes. Now, notice that they both are downward sloping. This is as a result of allowing the ball to move in the negative x direction. That could be manipulated, for instance, to be the positive x direction is to the left, in which case it would have the same slope but in the first quadrant. Now, you can see there is some discrepancy between the experimental position and the model position. This could be caused by a number of outside factors with the experimental case, such as friction with the ground, air resistance. There are other outside factors causing it to not have a true net force of 0, thus potentially decreasing the speed. The model provides a more accurate, constant velocity picture of the physics that we are trying to present. That being said, it is very linear. It does very, very closely model the Python simulation and is a strong representation of a real-life application of constant velocity. So in conclusion, we have now observed a real-life example of constant velocity and have seen how it applied to Newton's second law of motion and the formula for evaluating final velocity. Now, as you derived here that the final velocity was equal to the initial velocity, but to confirm that it is constant across the entire time interval, aside from the graphs and the data tables, a simple physics principle way that you can calculate that is by looking at the average velocity, which is the average of the initial and final velocity over the period of time, which, as you can see, the average velocity is equal to the final velocity is equal to the initial velocity, so the velocity thus stays the same across the entire time period and is therefore constant, thus reinforcing these fundamental principles of physics.